All right, this is the demonstration for simulating ecological processes, or the fourth lesson in our coding series. So simulating ecological processes is relatively simple in R if we have the right ingredients. And the main ingredient for doing this are what we call loops or for loops. Loops in R are a fairly efficient way to perform repeated actions over a defined sequence. So in other words, you're telling R to reiterate a certain action over the length of a vector or a certain number of rows or elements of a list or whatever. And these for loops always follow a fairly basic syntax that starts with for, hence the name for loops. Then have a variable that usually denotes the iteration. This is usually a single letter, I, J, V, and that are then enclosed by curly brackets. So what this looks like in theory, you can ignore all of this for now. This is just me loading the tidyverse package because we'll need it later. But this is your actual for loop right here. So it says for the letter I in 1 through 8, and then you get your curly brackets. And then I only have one function here, which is to print I. So print this variable. And that's exactly what it does down here. So in other words, I'm telling it that for 1, 2, 3, 4, 5, 6, 7, and 8, I want you to just print that number, and that's the result of it. So that's obviously pretty simple, but it's also not a particularly useful application of these for loops. So let's have a look at a slightly more useful loop. So one thing you'll often want to do is actually reiterate a certain action over an existing data frame or a list or something like that. And oftentimes you will actually want to store the output of your loop in a new object because it runs iteratively. It basically overrides the previous element of the loop every time unless you store the output of that loop somewhere in each round. So what I'm doing below is I'm creating abundance data for actually 4 different bird species over 10 years. Obviously, it's completely made up, but it does the trick for this example. So I'm creating an element that's called bird list first, and it has 4 different bird names: shearwater, albatross, penguin, and booby. And then I'm specifying that the number of years shall be 10. And then what I'm doing right here is I am creating lambda values. So that's just one of the values that the Poisson distribution takes to create random values. You don't necessarily have to be too concerned about this. Just know that I am creating this right here. Okay, and then the other thing I am doing is I'm creating a target data frame, or in this case, a target matrix. This is so I can store each output from the loop in an element where it actually will persist and not be overridden by the next iteration. So the way I'm doing this is just using the matrix command, and then the number of columns is the length of the bird list right here, and the number of rows is the number of years, so 10. And then I'm just giving my matrix names so that the 4 birds are actually the column names of that matrix. And then here's the loop. It's not a lot of code at all, 3 lines of code to be precise. So what I'm saying is similar to the previous one. I'm saying for I in 1 through the length of my bird list. What does that mean? That means for I in 1 through 4. So basically I'm specifying that I am going to have 4 iterations in this loop because the bird list right here has 4 elements. Then I open the loop right here. These are the curly brackets. They close down here. So everything in here is in the loop and will be done 4 times. Then I'm creating within the loop an element called x, and x is a number of random integer values drawn from the Poisson distribution. It has 10 elements because I want 10 years. I could have set num.years here instead, but I just wrote it out to 10. And then I'm taking the ith element of lambda. So in round 1, it's going to take the first lambda value. In round 2, it's going to take the second lambda value. In round 3, it's going to take the third. And in round 4, it's going to take the fourth. And then within the loop still, I am specifying that the first column of my bird target data, and remember this data frame we made right here, the first column should be filled with x. X is right here. That's the random distribution of values that I created with lambda I. And then I close the loop, and that's it. And this is the output. I get beautiful distributions for the 4 species that are arranged the way I want it, and that came from my loop. Could I have hard-coded this out and just, basically created 4 different distributions and added them manually to this data frame? Absolutely, but that's not the point. The point is that we can efficiently tackle some of these iterative problems by coding loops, and once you get the hang of how to code a loop, it's often actually a lot quicker to do it. The way I always like to think about it is if you have a problem in R that requires you to copy-paste the same thing over and over and over again, you might want to think about whether it's easier to sharpen the saw or sharpen the axe before you cut down a tree, or if you just go out chopping trees down and don't worry about sharpening the axe. Okay, so let's have a couple of words about the actual process of numerical or theoretical modeling. It's a different type of models that some of you may be more familiar with. So these are not statistical models. Statistical models are closed form equations that allow us to get quantitative predictions of the effect of X on Y, whereas numerical models are essentially just a tool to understand some of the most complex and dynamic processes in nature, and they usually involve some kind of time-stepping simulations to explore these dynamics over time. The good news is they're usually more or less made up, so they're really just there to explore what may happen if conditions were such and such. And as such, they're applicable to practically all species in any ecosystem, including there's an interesting example of Daisy World. This is a scientific paper that Lovelock wrote in 1992. It's published in the Philosophical Transactions of the Royal Society, a pretty good journal. And Lovelock basically just made up a new planet called Daisy World that had certain environmental conditions, including solar radiation, and he explored some of the biodiversity trends in Daisy World or on Daisy World through numerical models, and you can see some of the modeling efforts there. Now, the model that we are actually going to play with is called the Moran model, and it comes from population biology, as so many of the other things we've dealt with so far. And the Moran model is a neutral, closed community in which no evolutionary forces are at work in principle. So the neutral here suggests that we have no selection going on. All species are equal. The closed means that we have no dispersion for now. and then no evolutionary forces means we don't have any speciation. So it's really just ecological drift that we're concerned with here. And the way the model works in this most basic form is you start with an initial community of J individuals that are divided among S species. And for our purpose, we're always going to deal with 2 species in these simulations. Within this community, you select one random individual that is going to die, poor thing. And then you replace that individual. So the number of individuals will always stay the same in the community because you're immediately replacing it. You replace that individual by selecting another individual at random to reproduce. And that replaces the casualty. The only thing that determines the likelihood of whether a species is going to reproduce is the number of individuals that species has in the community. And then you just rinse and repeat that same process over however many time points you want. And you can already see how a for loop would be a very good way of dealing with this. Okay, deep breath. You don't have to necessarily understand or digest every single line of code in this, but I'm going to walk you through nonetheless. And this code was something I adapted, slightly rewrote some of it, mostly to give me the ability to work with more tidy data in here. But it's based on the code that is presented as an accompaniment to Valent 2016, A Theory for Ecological Communities. You can click that link if you want to get there. Okay, so the first thing we're going to do is we're going to specify the number of simulations. This is how many times we actually want to run this model. Oftentimes we want to run these models a few times because the outcomes may differ, and we want to know what the range of different outcomes can be. So in this case, we're setting this to 20. And then we're specifying the number of years. So this is the number of years that we give each community to observe some of the dynamics. And then we're creating a matrix for our output. So I'm calling this freq1 mat, which stands for frequency of species 1 matrix. And it is a matrix that has the number of simulations as columns. So this is the number of communities that we're simulating. And it's 20 in this case. And the number of rows is the number of years. So in each community, we have 50 years. And that is our matrix that is going to save all of our results. Okay, so now we're getting into the loop, and we're actually having nested for loops in this. And we're going to start with this first one. And the first one is for the different simulations. So for the different communities. This is to repeat the same model for 50 years across these different communities. As such, our initial line of code here reads for j in 1 through the number of simulations. So this is for j in 1 through 20 because our number of simulations is 20. And then the first thing we're doing is we're specifying that we are working with 100 individuals. We could have specified that outside the for loop as well if we wanted to. We're then creating a value of abundances of species 1 at time point 0, and that is half the community in this case. So we're just assigning this, and we're then doing 0.5 times j, so 50 individuals are of species 1. And then we're creating our community by simply producing a vector that has the length j. So this is a vector that has 100 elements. And then we're assigning, in this vector, we're assigning the first 50 to be species 1, and then the second 50 to be species 2. So this is all just set up right here. And then we are setting the year to be year 2, because the first year is always our starting point, and then we want to move on. So the first year we actually want to switch to is year 2. That's why this is year 2 and not year 1. And then we are simply filling this community matrix with the sum of the individuals that are J, or the frequency of J in this community. So the entry of J, so the different simulation here, will give should be the frequency of species 1 in the community. The second loop then is the one that actually reiterates over these individual death and birth events, and that runs over multiple years. So again, this one just does separate iterations of the same model, and then the model is right here. So here we're now saying for I, and I'm using a different letter because I have to, otherwise the model would get very confused. For I in 1 through J times the number of years minus 1. This is to get iterations for each individual in each year, okay? And then I've got my winged brackets again, and then I am first determining the frequency of species 1 in this community as of right now, okay? And then I'm assigning probability 1, this is the probability of reproduction, to be the frequency of species 1. So I'm saying that species 1 will have a probability of reproducing that is equal to its frequency in the population. And then this code here gets a little complex, but all you really need to know is that this is where all the magic happens. I am essentially, here I am randomly selecting an individual to die, and this works by picking a random value between 0 and 1, multiplying it by J, and then rounding it up. That gives me a completely random number that may, for example, in our community may be number 52 or number 58 or 23 or whatever. And that individual is the one we have selected to die. And then we are replacing it here with this line of code. And this line of code simply says that I want to replace it with either a 1 or a 2, and the probability of it being 1 or 2 is based on this probability right here, okay? And then this is the final bit of code in this loop, and it essentially says that when the iteration is divisible by the number of individuals and there is no rest, so the rest is 0, then I want to record it. And basically what that does is it marks the end of the year. And then right here, I'm just saying that the row in the year column should be filled with the frequency of the community of species 1 in the community right then and there. And then this is an important step because I'm now here telling it to move on to the next year. So I'm just saying that year is now the previous year plus 1. Whew, deep breath. It's complicated. Trust me, you don't have to understand it all or know exactly what each line of code does. You just need to be able to roughly orient yourself in this code. And then there's a little bit of code afterwards here. I am setting after I've run all the loops, I'm setting the column names of the frequency 1 matrix to be 1 through the number of simulations. So they're essentially just, making sure that my columns are named 1 through 20. And then I'm adding a column here to this data set, turning it into a data frame, and then adding a column that has the number of years. And this is just 50 rows from 1 through 50. So let's take a look what that actually produces. This is just the head of that data frame, so only the first 6 rows. But you can see that our column names are 1 through 20. There is a column named year that goes down in numbers or up in numbers. And then in each simulation, so in each community that we've simulated, we have these values of the frequency of species 1. So this one moves from 50 to 49 to 57 to 60 to 47 to 40, and so on and so forth. This one, number 2, the second community, actually goes on a pretty quick plunge, not looking good for species 2 here. It goes from 50 all the way to 92 within only 6 years. So you can imagine that by the time 50 years are over, species 2 probably will be extinct. Now, because we like tidy data, we will want to process this data very quickly. This is what we're doing here. So you're using dplyr to turn this wide format into long format. It only takes one line of code, really, right here. It takes the gather function where we're gathering columns 1 through 20, and we're calling the key iteration and the value frequency. And then we are plotting this using ggplot, where the x-axis is our year, the y-axis is our frequency, and then we're grouping this, and this is important. You have to specify that the group is the iteration. And then I'm using a geom line right here, which draws a line based on the group that you're working with. So the grouping argument here is important for the geom line. And then I'm just specifying a scale color gradient where I'm going from this purple color right here to the golden color up top, and then just specifying a couple of aesthetics. You don't necessarily have to do this, but it just makes the plot look a lot prettier. And this is what we get. It's a beautiful simulation of the Moran model, a model that only considers ecological drift, random walks to extinction by species in the community across different communities. And you can see each line here is a community. We have years on the x-axis, the frequency of species 1 on the y-axis. When we're up top here, these communities, species 1 has prevailed, has outcompeted species 2. Species 2 went extinct, took a random walk to extinction, and vice versa down here. And in these communities that are in the center, you still have some kind of coexistence, but it's probably not going to last all that long. Okay, so what if you want to change model parameters? It's as simple as changing a single number in your big, giant, clunky loop. You just have to know which number it is. So in this case, let's change the number of individuals in our community. So that's J, remember that, to 1,000 individuals, and the number of years that we're simulating to 100. The number of years, we're changing that number right here. So that's 100 now. And then the number of individuals, J, we're changing right here. So that's 1,000 individuals in this loop. And then we run it. And then we do the exact same thing we did earlier. We add the column names, we add the year column, we gather it, we plot it, and this is the output. Because we have more individuals, we're less likely to see actual full extinction in the model. We can see that in most of the communities, actually I think all of the communities, this one got close, but in all of the communities, both species are still prevailing even after 100 years. After 50 years, we're in pretty good shape in all of them. But you can also already tell that if we would have done this for 150 years, we probably would see the same random walks to extinction that we saw in the other model. And that is the T for now. So it's fairly simple. All I'm asking you in this exercise for now is to just familiarize yourself a little bit with these loops, and you can try to maybe code one out for yourself as well. And then just to change a couple of values, run the model, and gain some confidence and knowledge about how this model behaves when you change certain values around. And we'll leave it with that.